It's always a pleasure. Yeah, I'm going to tell you about a really work that I like, which gives this nice new connection between quantum machine learning and complexity theory. So it's based on a joint work with Srinivasan Arunashalam from IBM Quantum, Alex Gurillo from CNRS, Igor Oliveira, who is also in Warwick, and Arti Sundaram from Microsoft Research. And it's also based on some ongoing work. So let's just maybe dive right into it. So let me tell you about the plan. This for me, I like talks which are chunkable. So we'll have 5 parts. Each one of them will be self-contained and less than 10 minutes. So if you snooze in one of them, you don't have to miss the other. And the idea would be we'll start by just first talking about the main message and just what are we doing, why are we doing, and why I think you should care. And then I'll give you my perspective, outrageous perspective on circuit lower bounds. So at the risk of upsetting some people. And we'll talk then about quantum learners. And I want to say first, I assume no preliminary knowledge in complexity theory, and similarly, no preliminary knowledge whatsoever in quantum computing. So we'll talk about what does it mean to have quantum learners and what they can do. And then I'll go tell you about this new connection between circuit lower bounds and quantum learners, and finish by telling you the main ideas, the main that goes in this work. Okay, so let's start part 1, the main message. So for me, this is the most important part of the talk. I think that there is an important goal here, and hopefully I can get some people interested in pursuing this vision. So what are we doing and why? So I want to start with the big question, which is also the title of this talk. And essentially the setting is as follows. We all know that quantum is on the rise. We've seen millions of dollars being invested in it. And recently we had the experiment of Google, which showed quantum supremacy, and it's clear that we care a lot about quantum computing. And on the other hand, if we are thinking right now, then we already know that machine learning is changing our lives. We use it for everything, for vision. We plan to use it for automated cars. It's something which one of the most important paradigms in computation. And so one doesn't have to be too creative to ask the question, can we use quantum computing to do machine learning better? And this is a question that bothered me for a long while. And the reason being is you have something which is so well motivated, but yet to the best so far, we have no example of provable strong quantum speedup for learning. And so there were some works which seemed to be the case, but then later we found out that this type of learners, quantum learners, can be emulated classically. And so it still remains open, this question of, can we get quantum speedups, any quantum speedups, for learning classes which, not degenerate, classes which are somewhat expressive. And what we do, so is we establish this new connection between these seemingly 3 different fields. One of them is that of quantum algorithms, where we ask ourselves, how can we solve computational problems faster using the power of quantum mechanics? The other one is learning theory, which is the theory which underlies machine learning. And the last one is complexity theory, which studies the limit of computation. So somehow, and it even surprised me that such a connection exists between all of these two things before I started working on this problem. But we show that there is a tight tri-directional connection here. So let me kind of jump to the main points. And that's the take-home message, my most important slide. So essentially what we prove is take the, trivial quantum algorithms, which achieve, essentially like just the mere, essentially what classical algorithms can achieve. I'll define trivial soon in a more coherent way. So if we make any tiny improvement on these trivial learners, then this would imply breakthrough results in complexity theory, which would imply really interesting circuit lower bounds that we have been trying to obtain for a very long time. And now the way to interpret that, it's very much depends whether you're a glass half full or a glass half empty kind of person. So for an optimist, you can say, well, this is quite exciting. I mean, we want to prove these circuit lower bounds for a long time. We want to show hardness of computation. And now we can use the power of quantum information. We can use algorithmic design in order to, to get this like fantastic circuit lower bounds. A pessimist, on the other hand, can say, well, we know that circuit lower bounds are notoriously hard to come by and to prove. And so if you've been wondering why we don't have quantum speedup, provable quantum speedup, then, well, it's no surprise because they would imply these circuit lower bounds. So that's the main message. And in the next 10 minutes or so, I'll try to give a bit of intuition as to why this result holds and why it's interesting. So we're continuing to part 2, circuit lower bounds. And I want to give a very simplified perspective on this entire super important endeavor that we do in complexity theory. So, it's not often that we can literally talk about $1 million question, but that is the case with P versus NP. It's funny, typically we think about P versus NP as this question of asking, well, we have the class P of all problems which are solvable in polynomial time, and we have the class NP, which are all problems to which we can verify the solution in polynomial time. But I want to advocate a slightly different perspective or a slightly different interpretation, where by P we capture the tractable problems, and by NP we capture essentially most problems that we care about. So the question of whether P is equal to NP can be viewed as, if we think about most problems that we care about, can we do them in an efficient way? And by the way, I want to use this as an aside, that there is to say something about complexity classes. So it's something I heard Scott Aronson say, and it really resonates with me. So he said at some point that physicists are really good at coining impressive terms for fundamental phenomena. So you have the Big Bang, you have black holes, supernova, it all sounds so exciting. And we, in complexity theory, we have BPP, BQP, and it all sounds like acronyms of airplanes, airports, and stuff like that. But I want to stress that while this talk will have quite a bit of acronyms for complexity classes, these classes captures fundamental truth about the nature of the universe, about whether the universe is deterministic or randomized to a computationally bounded observer, about many fundamental questions that we ask ourselves. Okay, so we since the early days of computer science, we've been trying to ask this question of P versus NP. And quite quickly, we came to the conclusion as a community that this is an extremely hard problem. And it wasn't really clear how to even make progress on that, because Turing machines are extremely hard objects to reason about. In fact, we can prove that finding properties about Turing machines is often can be completely intractable, and in other cases, it's just extremely hard. So There is one approach, which is that of circuit complexity, which aims to, at least naively, reduce this complexity. So what is the idea? While Turing machines are complex machines, we can instead think about another model of computation, which is quite similar. Well, we just think about circuits, we take gates, we take wires. And the benefit of that is now that we're talking about combinatorial objects, there is nothing mysterious which gets, constant size description machine, which gets whatever size of input and somehow processes it in using this infinite memory tape. It's just about counting gates and wires. And so, if we think about circuits as graphs, we say maybe we can use all of the tools that we have from combinatorics to make progress on the problem. So that's at least the high level, approach in circuit complexity. And I should mention that a circuit could just easily be quantum. In fact, in the quantum setting, when we think about circuits, this is the main, by far, the main model of computation, because nobody wants to work with quantum Turing machines. And I want to say, to kind of express the point that circuits are a non-uniform model of computation, in the sense that whereas with a Turing machine, we can deal with any input size, a circuit, we fix an input size and then we need to work with it. So I'll make this notation here. But whenever we have a class C, I will just use Sn to denote what is the size of the circuit. And the size of the circuit, it could be the number of gates, the number of wires. We won't really care about this type of distinctions. Okay, so first thing to ask about the model is, can we prove some hardness result using that? And I want to talk about this paradigm of structure versus randomness. I'll give the simplest example right now, and later but we'll see this will be a recurring motif throughout this talk. So, we transitioned from Turing machines and now we're moving into circuits. And there's this question of, do we have any problems which require circuits of super polynomial size? And unlike with Turing machine, when this is not an easy problem, here we can do a simple counting algorithm. So we can say, well, how many Boolean functions we have? Well, we just count the total number. It's 2 to the 2 to the n. And then we say, let's look at all polynomial size circuits. So we need to look at polynomial many gates, and we can give them assignments, and we can think about all the way that we can wire them. And now it depends on how many gates you allow in the precise model, but in all reasonable models, there are far, far, far fewer polynomial size circuits than functions, which means that the absolute vast majority of all functions are extremely, extremely, extremely hard for computation. And this again goes to tell us maybe something about this perspective of NP being the problems that we care about. So if you think about it, this says something about human nature in a sense. So you'd think that if the fraction of problems or functions that can be computed efficiently is something which tends to zero extremely fast, then no efficient algorithm would exist, or for problems that we care about. But somehow this is not the reality. And it turns out that human being cares about extremely structured problems. We don't care about computing extremely complicated functions. So the things that which appeal to us of use and of interest to humans tend to be these extremely structured functions. So this is just at the beginning of this tension of structure versus randomness, where, for example, showing that a random function is hard, that's very easy. We show a proof in a minute. And in some sense, finding an explicit function which is hard, explicit function for, that we care about, maybe a function that could be in NP, that's like the unicorn of complexity theory. It's something that we all seek, and that's the main goal of all of complexity theory. Okay, so Now, I want to tell you about circuit complexity as an endeavor. So back in the 80s, things were really, really good. You could turn the radio and hear Nina Simone singing, "It's a new day, it's a new dawn, and I'm feeling good," because circuit complexity was in a meteoric rise. So it started by saying, well, we have this model, so let's see if we can start by proving something. So we restricted our attention to a class which is called AC0, and that's constant depth circuits. So it really, really, really restricts the amount of depth of computation, the amount of steps that you can do. You have to do everything extremely in parallel. But already there, unlike what we had with Turing machines, we can show this bound that for the parity function, which is just like computing the parity of a string, you can't have any poly-sized constant depth circuits. So this was a true progress. However, one could say, well, this is not reason to go out to the street and celebrate, because, I mean, it's parity. It's a function which is clearly easy to compute. So this goes more to show that constant depth circuits, this AC0 class, is extremely weak, as opposed to say we prove extremely strong lower bounds. But then came this result by Rasborov in 84. And essentially it told us that the click problem, it's a problem that we care about, it's an NP-complete problem. So it's not in monotone NP. And I want to say a bit more about this problem, because I think I'm imagining, if I were alive and relevant at the time, this would be something which is extremely promising. Why? Because we have click. It's a really important problem. It's a really hard problem. It is also a problem which is monotone. So what is click? We have some graph and we want to know whether whether there's a large click in it, a large set of vertices where everything is connected. So this is a monotone language, a monotone property, because if you have a class and if you have a click and you just add more edges, then you remain with a yes instance. And now, what is monotone P? You can consider these circuits which don't have not gates, and therefore, if they accept a string X, then they accept any string in which you flip more ones. So it's there is this like natural correspondence between two notions, and a priori it could have been the case that really, now Rasborov proved that you can't have poly-sized circuits for click which are monotone, and because click is monotone, then this should imply the whole thing. Of course, this turned out not to be the case, and sometimes you really do need. There's a lot of thing to gain by having non-monotone circuits for monotone problems. But still, the progress continued, and we found a way of showing exponential size AC0 lower bounds, and then also for click. And we extended beyond AC0. We added some parity gates, and it just seems very, very, very promising. However, then the 90s came, and from here things went mostly downhill. Though some would maybe disagree with the statement, but I think everyone would disagree that the pace dramatically reduced and the approach seemed far less promising. It felt that as a community, we're kind of running in circles, trying to somehow, make some progress, but nothing really works. So for example, the belief that we have is that P-poly, which is the size of, this is just another name for all polynomial size circuits, that it doesn't contain NP. You can think about it as the P versus NP analog of circuits. So we really strongly believe we have, complexity, doomsday implications of what this happened, that this is not the case, and it's consistent with our intuition that the mild power that we're giving circuits with this non-uniformity, then it still should be far, far, far weaker than NP. But while we want to prove such a statement, what we actually know is almost embarrassing. So for all we know, it could be the case that not only NP has polynomial circuits, but even exp, which is everything exponential. So if by NP I said this is most of the things that we care about, then X for me represent the class of all problems that we can even think about unless we're trying to be, smartest about them. And then NX goes even beyond that. It's a non-deterministic. So even that huge class, we can't prove that it requires super poly size. And in fact, we can go far worse than that. Even if we allow this exponential time and we are quantum, this is what is captured by BQE. It's just a quantum name for a quantum exponential time computation. So not only it could have polynomial size circuit, it could have this extremely depth to circuits with just like this majority gate, something which is extremely, extremely, extremely weak. So this is not so good. And I say just a couple of words about this, depth to circuits, threshold circuit, because in some sense, this is the threshold, both in learning theory and in circuit complexity. It's a frontier, kind of like illustrate what we don't know. And this is also a class for which we have some application, so I can tell you about it. So what is TC0? It's another, I think it's the last class that I'm going to introduce. It's taking these constant size, constant depth circuits and just augmenting them with majority gates. So still, if you think about it, this is an extremely limited model of computation. It captures essentially, what you can get inside polytopes or something like that. But somehow we still don't know that we cannot solve any, polynomial time problem using these TC0 circuits. So this is something to keep in mind. Okay. So the last thing I want to say about circuit complexity is, well, we can conclude that we know that circuit lower bounds are hard to prove. It became almost something, as a reason to stay clear of a problem. Suppose we know that the problem reduces with, if you solve X, then it would imply circuit lower bounds, then it means that probably you're not going to solve X. And it got into the place where things are so difficult that when finally in 2011, Ryan Williams showed that this ACC0 class, which is constant depth circuit, when you add these mod gates, doesn't contain NX. This was a major breakthrough. I remember, I think it was my last year of undergrad studies, and I heard like lots of the graduate students saying, wow, there's this amazing paper, and I really was excited to see what this is all about, and just to learn that it means that we can't have NX, this huge inconceivable class within this small class of circuits. But something in addition to this major breakthrough, that there was a new paradigm, a really interesting one, which is this big idea that we can use positive results. We can build algorithms in order to derive circuit lower bounds. Okay, and that's going to be the focus of what we do. And we'll do this for specific type of algorithms, which are quantum learning algorithms. So this is where we are going to talk about quantum learning, and I will abstract most of the quantum away, but I will leave the relevant details. So what is quantum learning theory in a sentence? Or maybe let's start with just learning theory. So we have this algorithm, and suppose that we want to have this task of distinguishing, whether a certain image is, a picture of a cat or not. So we can think about similarly just having an algorithm which does this task. We can also have a quantum algorithm, which gets this image and decides whether this is a cat or not. And to make the discussion slightly more formal, the vanilla model in which we represent this type of learning algorithms is called pack learning. And the idea is that we say, well, we have this, maybe let me just add a small drawing here. So we have this class C, and there is some function f within this class C, and we want to we have the promise that the function belongs to C, and we want to find out which of the functions in C is the function that we want using just samples from the function. And we can't do that in general, so we make this probably approximately correct condition, which is probably the worst name in terms of marketing, like getting solutions which are probably approximately correct. But it means that we get samples, and using these samples, we need to output with high probability some circuit which is a good approximation of this function. Okay, so we allow slackness both in terms of how well we approximate the circuit and what is the success probability. So for the rest of the talk, I kind of think about the success probability as being, high, let's say 90%, and we'll only care about how good of an approximation we can get. Question?
Yeah, Tom, so here we have random queries to have.
Yeah, so here I'm talking about the complete vanilla setting and think about maybe even classical algorithms, just pack learning sample to F. And in some sense, this is kind of preparing the ground for what I want to say next. Is we want to show this connection, which says, if you manage to design an algorithm that does something, then you get a lower bound. So it is in our advantage to make this algorithm as powerful as we can, because as the stronger the algorithm is, then the more expressive it is, and maybe we'll be able to design a learner, and in turn we'll get the circuit lower bound. So we're going to take this and extend it, like strengthen the model as far as we can. So what do I mean by that? So we'll do the following changes. And please ignore the notation, all of the heavy notation at the bottom. It's not really important at all. So what we're doing is first we say, as Sasha mentioned, rather than having samples, let's allow queries. And not only queries, we can make these quantum queries. So what is a quantum query? Essentially, it means that we can query in superposition. So think about it. In a single query, we can download the entire values of the function into some quantum state. But as with everything quantum, we have all the answers in the world sitting in few qubits, but we can't see them. We have to measure, and then it collapses into only classical strings. So it requires, it gives additional power, which can be extremely useful, as we know, for example, from Shor's algorithm. But it's not as direct as just having all the answers, all exponentially many options written down. So the first thing, this is we augment the model by having query access, which is also quantum. And we also allow us, instead of giving some hypothesis, which tries to predict the function, we can output this quantum circuit. And this quantum circuit, so this whole expression that you see here, it's just quantum notation for saying that you have a circuit, and once you measure it with extremely high probability, it would approximate the function. So this is how we augmented. We augmented both having quantum access and the ability to output quantum hypothesis, which both are potentially more expressive. Now, an immediate question to ask is, so we gave this power, but can it help us with it? Are there any reason to think this could help? So on the one hand, we know that quantum queries could be extremely powerful. We have exponential separations for particular problems in the query model. So we do know that quantum queries have a lot of potential. But in the learning setting, very, very little is known. So it's not clear what they can do and not. However, there are 2 points that I want to stress. One is that we have lots of negative results in the classical setting, which no longer hold now in the quantum setting. So any negative result the vast majority of negative results we have for learning do not extend to the classical setting, to the quantum setting. And on the other hand, there are some amazing, amazingly non-trivial quantum algorithms that admit speed that you wouldn't think are possible. And maybe something as famous as Grover's algorithm. If you think about it, it means that you can take the SAT problem, and it admits some algorithm which is does better than brute force, which is quite surprising. So it is plausible that we might get some advantage using that. And our fundamental question is saying, can we do anything using quantum learners? So can quantum learners get us this type of quadratic improvement as we get for SAT? So for example, just to say, suppose that we have a TC0 circuit. We know nothing of how to learn non-trivially this class, but can we get even tiny improvement using the quantum algorithm? So now we're finally getting to the interesting part, which is this new connection, which essentially would say just that. So that's a theorem that we're proving. So let me try to break it down slowly. So we're starting with this circuit of polynomial size concept. So take any class of poly-size concept. And now what I want to say is, suppose that we can learn them with error, which is, let's say, half minus gamma. So what do I mean by that? We can always learn a Boolean function with L half just by random guessing. So this is not interesting. So think as gamma being saying, can we get any advantage, tiny advantage over completely randomly guessing without looking at the function at all? So what we say is that if you get this tiny improvement, and you can do it in time which is just slightly less than exponential, then we'll get this, this circuit lower bound of the type that BQE would not be contained in that class. And I will give some concrete examples in a second. But just to say, this is, as far as I know, one of the more exciting things about this for me is that this is the first connection that shows of the form that says, give me a quantum algorithm, and in turn you'll get some complexity lower bounds. So a way of getting new circuit lower bounds via the design of the quantum algorithm. Okay. And just to give this concrete example, going back to these threshold circuits. So suppose that one can take, if one can design a learner for TC0, for this depth to threshold circuits, if you can take these circuits and learn them in time, which is just ever so slightly less than exponential, then this would already imply, be a major new circuit lower bound that would imply some major progress in complexity theory. So that's the main result itself. And I want to, before I tell you about how we show it, just to say something about the tightness of the result, because I mentioned this quantum level. Yes, Sasha.
So Tom, we have a similar results for classical learning algorithms, don't we?
Yes, we do. And these results directly, sorry, I should have mentioned, these results directly quantize the existing result that we have in the classical setting.
But they're like essentially of the same form. If you have faster classical pack learning, then you get the corresponding circuit lower bound. Except
yes, and the circuit lower bound is for a classical class.
Would it be E or X, or is it like BPE or something?
Yeah, BPE.
Got it. Yeah, thanks.
Yeah, so to say, going back to this point, I said if we do better than a trivial learner. So I just want to give an example of what do I mean by trivial learners. So there is one trivial learner, which is also a trivial learning in the classical setting. It's completely not interesting. It says, well, query everything, right? So if you query the entire truth table of the function, then you get a perfect prediction, and the error is T0. So this is like a completely degenerate condition. Just say, you won't get an exciting lower bound if you do that. That, of course, makes sense. However, there is also something that can be done which is less trivial in the quantum setting, which is obtaining like a polynomial time algorithm that can obtain error, which is, the advantage over a random guess is roughly 2 to the minus n/2. And so we can get a tiny, tiny, tiny improvement for any class always in the quantum setting. And I can just give a very brief idea of why this holds without getting into quantum details. So there is a very famous quantum algorithm. It's called the Fourier sampling quantum algorithm. As you see, it's a really simple algorithm. Essentially what we do is we put the input in a uniform superposition. We do this query, which I mentioned, which downloads all of the data, all of the truth table into one state. Then we apply another layer of Hadamard gates to apply the Fourier transform, the Boolean Fourier transform, and essentially we measure. And so this is just, I just like mentioned the circuit. But what this circuit is doing, it has the effect of giving us a Fourier coefficient with probability that is proportional to its weight. So I will see a certain label of a Fourier coefficient with weight which is roughly squared that of the Fourier coefficient. In other words, it's a way of efficiently sampling a very heavy Fourier coefficient. And because a Fourier coefficient is defined as the correlation of a function with a certain Fourier character, then this can give you an example of a learner. So what you do is you run this algorithm, you get this heavy Fourier coefficient, and this heavy Fourier coefficient, by the way, when I'm saying heavy, I mean non-trivially heavy, of roughly such weight. And then this Fourier defines a Fourier character which is non-trivially correlated. So this gives the trivial thing. So essentially, a simple way of saying our result is suppose that we do something which does better than these two things, like read everything or do this generic thing which works for any class, then you'll get these new circuit lower bounds. Okay, and in the last 10 minutes, I'm just going to tell you about the key ideas that are going in order to make this result happen. I'll try not to get overly technical, but just present the main conceptual ideas to give some sense of why this result holds and how. So here's the proof overview. There are 3 steps, and I'll try to do it extremely like slowly and as coherent as I can. So I want to start by saying, first of all, there is this notion of natural properties. This is one of the most like natural way of proving complexity separations. So what do we say? We want to show, I mean, if you think about it for the first time, how is one supposed to prove something that, like, that there is no algorithm that can perform a certain task? It seems as if one needs to consider all possible algorithms in order to do so. And this is not something that we can do. So a very natural approach would be to say, here is a property of an object of so for example, let's do this, the AC0 example. So for example, you can say, if I have a random function, which is complex, and I do some random restrictions to its inputs, then it would remain a complex function. And if my function was really simple, maybe it can be represented by a constant depth circuit, then it would get completely degenerate after applying these random restrictions, which means that this gives us a way of differentiating between complex functions and simple functions. So the first step of what we're doing is we're showing this theorem, which shows that you can take any quantum learner and get from it a quantum analog of this natural property. So what is this quantum analog of the natural property? Let me just say exactly what is that. So the important thing to keep in mind is that picture. So it's just an algorithm that can distinguish between a class of the class that we care about and some random dense set. So it rejects functions which are inside the class, and it accepts this dense set, and we have a third condition that it runs in time, which is polynomial in the size of the description of the function. And the way of thinking about it, just the way I can kind of conceptualize it, is having a quantum natural property is a way for us to distinguish between structured objects and random objects. So that's like, and in some sense it's quite intuitive. If you think about it, if you can learn a function, then at least you can think that it means that you can understand something about its structure. It can be completely random. And there is this idea that this would be, so just like to say how, so how can we show something like that? Then how can we derive these quantum natural properties? How we can distinguish between C and this dense set? So the idea is that if you have a quantum learner, then you can just apply it to something. If you happen to be in C, then you will get a good hypothesis, and that hypothesis will be a good approximation of your function. So you can kind of like just compare it to your function and sample and compare, and you can see that you are in a good place. Whereas it's not that hard to show that if you are in this dense set, if you're like a random function, then with high probability, the learner will not give you anything which is correlated with the function. So this is like the high level idea. Okay. So this is step number 1. Then comes step number 2, which is the main technical contribution that we're doing. So we're showing a conditional pseudo-random generator that can fool quantum circuits. So let me kind of do it step by step. So first of all, what we're assuming, we say, suppose that there exists some function in P space, in polynomial space, that doesn't admit sub-exponential quantum algorithms. So under this assumption, this gives us a hard function, and using the hard function, we can derive from it some pseudo-random generator that can output strings that no quantum circuit can distinguish between something random. And this is, to the best of my knowledge, I think this is the first conditional pseudo-random generator that we have against uniform quantum computation. And the type of techniques that go through it is analyzing the localist decoding of IDKW and extending it to the quantum case. So this is the rough idea. And then comes the most interesting part, which is part 3. Well, we want to show unconditional circuit lower bounds. And so far, we have this conditional, like we have this assumption whether there exists this PRG, we have this PRG only if, something holds. So what we do is this nice thing, which is called the win-win argument. And the idea is we kind of like say, well, if this assumption holds, then we get a lower bound. And if this assumption doesn't hold, then we still get a lower bound. So the reality is that we don't know which one is the case. Like we don't know whether the assumption that we have holds, and therefore there exists a PRG, and we can use this PRG to get a lower bound, or whether it doesn't hold. But we know that in either case, we can just get a lower bound. So what are we saying? We're saying that if there exists, for every problem in P space, we have sub-exponential quantum algorithms, sub-exponential quantum circuits, then in fact, this gives us, this reduces then one can obtain like a lower bound by a simple, 60s type of techniques of diagonalization. Essentially, it means that BQE, like that quantum exponential time is so strong, so much stronger than P space, and we can just do simple techniques and get a lower bound. And if not, then we have the PRG. And now comes maybe a really nice thing of how do we use the PRG for fooling uniform random circuits. So we have these like 2 components. We have these quantum natural properties, and we have the PRG that fools quantum circuit. And there's a question of how can we combine both of these things to get a lower bound. And that's the last idea that I want to discuss. So we have this class C. And our goal is just to hit any function, like to manage to find a function which lies outside of C. So how do we do it? We take this pseudo-random generator and we use it to produce this huge exponential size truth table of a function. So we use the PRG to produce lots of functions. And now the point is that we want one of these functions. This is a PRG, so we can explicitly get these functions, but we want one of these functions to be outside of C. But this is where the beauty of natural properties come. So think about this green space, all of the things on which the quantum natural property algorithm would say yes. And the red part is all of the things that the quantum natural property would say no. So, sorry. Okay. So our goal in some sense is to manage to find a function explicitly that would lie in this green area. Because if the quantum natural property says 1, then we know that it belongs in this like dense subject, like it's definitely not in C, because like the natural property should reject things which are in C and maybe some other things and accept in the dense set. But the point is that once we're running the quantum natural property algorithm with the PRG, it cannot distinguish between a uniform random string and between something that the PRG output. And therefore, we can use it to hit a hard function and get it explicitly. So that's the high-level idea of what is happening. And yeah, and I want to conclude just by mentioning like 3 open problems that I quite interested in and hope to interest maybe some of you. So the first one is the obvious one. Can we design non-trivial quantum learners, right? Because in this sense, we get like, we hit 2 birds with 1 stone. On the one hand, we get this like really exciting new learner. So suppose that we manage to get just this meager improvement, this quantum algorithm, which does quadratically better in learning TC0 circuits. And think about it, that like getting in the quantum setting a quadratic improvement is not that a rare thing. So if somebody managed to do that, then not only we celebrate this quantum advantage in learning, but we also get this exciting new lower bound. Another thing is to ask, can we have quantum natural properties against other classes, and can we get into specific classes such as ACC0? This would have really interesting implications, both for natural properties as an independent study, as well as for like interesting circuit lower bounds. And there are some concrete directions that one can mention. I might discuss a bit later. And the last one is, we managed to get this conditional PRG, but it is a rather weak PRG. It's barely enough to carry what we need in order to have the bound. So again, it's quite natural to ask if one can obtain stronger PRGs, and in turn, this would also imply these exciting bounds. Okay, so that's the end. Thanks for all the attention.
Thanks, Tom. Can I ask a couple of questions?
Yes, of course.
So in your proof overview, I'm just wondering how much of the kind of classical stuff you can reuse. Do you have to redo everything? Say, yeah, step 2 here. It looks like in Polyatsev-Wigderson. Step 3 looks like quantum version of maybe Cleveland's Fortnell. Do you have to redo everything in the quantum setting, or can you like reuse the classical results in?
Yeah, that's an excellent question. So the answer is, we need to take each one of the components in the classical literature and quantize them one by one. Some of them happen in, even just first on a syntactic level, because you need to output some quantum hypothesis and you need to factor the quantum queries. But each one of these, but not all of these components are equally hard. Some of the parts are fairly straightforward technically, and some of them are extremely challenging. For example, when we want to construct the PRG, we're going through this like IJKW list decoding algorithm, and there is this which is quite an involved algorithm which talks about the Johnson scheme and the Johnson graph in general. And there's this one thing about quantumness, which maybe I should have said in the beginning. At least my view of quantum is as follows. You have deterministic, you have randomness, and then you have randomness plus plus, which is what you can do with quantum. And then there is one thing that we typically take for granted when we're doing, this type of argument, which is we can fix the randomness. So a lot of things that we do, we start an argument, we talk about a randomized algorithm, we fix the randomness, and this reduces it essentially to be deterministic. The noise is with quantum, you can't really fix the randomness. And in some sense, we actually introduced this intermediate model of inherently random computation, which is essentially saying, modeling this, suppose you have a randomized algorithm where you cannot syntactically fix the randomness. And that's where the real difficulty lies. Extending from this inherently random to quantum is not hard, but going from fixing randomness to not fixing it, that's the source of hardness.
Yeah, cool. Thank you. Yeah, also in your